Hello, video number 5 coming up, and in this video we'll take a short peek at finding future amounts from present values and present amounts from future values, future cash flows. And this is the beginning of our movement of cash flows from one point on a cash flow diagram to another point on a cash flow diagram. We'll look at the way we calculate those values. We will look at the notation that's used in the book, and we'll convert that then to the notation that we will use in our spreadsheets. So let's get right to it, and let's look at a spreadsheet. It's called FV, and by the time you see this video, it will also be posted to the classroom stream. Okay, here we have FV. Our annual interest rate here is 12%. We have a single deposit today of $100. We'll look at its value in a number of years in the future. So this first part, we should know how to do this. In 1 year from today, the value that we have in 1 year is equal to our $100 that we began with times 1 plus the interest rate, or $112. So we gained interest of $12, so that's 12% of $100, and now the total is $112. Now remember, in our language, that means $100 today at an interest rate of 12% is economically equivalent to $112 1 year from now. What about 2 years from now? Well, in 2 years, we take what we had in year 1, and we take that times 1 plus the interest rate again. So we can say that $100 today at an interest rate of 12% is economically equivalent to $125.44 2 years from now. So again, while we're compounding interest here and we're moving from time 0 to year 2, remember that we can essentially say $100 today is the same as $125.44 2 years from now. They are economically equivalent amounts. In year 3, we have what we had at the end of year 2 times 1 plus the interest rate, $140.49. That's all well and good. There are other ways we can calculate this. For example, in year 2, this is equal to what we had in year 1, which was 100 times 1 plus the interest rate. That's what we had at the end of year 1, times 1 plus the interest rate. That gave us $125.44. We can do the same thing in year 3. This is equal to what happened in year 1, 100 times 1 plus the interest rate, times 1 plus the interest rate, that gives us the amount we had at the end of year 2, times 1 plus the interest rate, gives us what we have at the end of year 3. Hopefully you can see a pattern here, and that pattern is our initial deposit times 1 plus the interest rate taken to the power the number of years in the future. So this is how we find a future amount given a present amount. The formula is F is equal to P times 1 plus I to the n. Some say that 1 plus I to the n is the single equation you need in engineering economy, and in a sense that's true. All the other equations, at least in the near term, are derived from 1 plus I to the n. Given that formula there, we notice that the notation in the book to find a future value, we have some tables that give us the 1 plus I to the n values, and we call those interest factors. And this would be F given P, I percent in years. That is, find a future amount given a present amount when the interest rate is I percent and the time is in years. However, whatever integer you put in there for n, and that's red, F given P, I percent for n years. Let's look at both of these here for another question. What is the value of our $100 in 15 years? 15 years down the road. Well, this would be equal to $100 times F given P. We're going to find a future amount. We're given a present amount. 12%, 15 years. That's the notation we would see in the textbook. This is going to be, we could look up F given P, 12%, 15 years, in the appendix, the discrete compounding tables in the back of the textbook. I won't do that right now. But this is equal to $100 times 1 plus I, 1 plus 0.12 to the 15th power. That will give us the same answer. And let's go ahead and get that answer. What is that? That's 100 times 1 plus I to the 15th. And I've made a mistake in my equation. There we go. $547 and something. That brings me to formatting. This doesn't have a dollar sign on it. It's got a whole bunch of decimals. The numbers you see here with the dollar signs is simply a formatting issue. The numbers are stored, they're safely ensconced somewhere, but we see them the way we want to see them in a spreadsheet. And I'm going to go up here to the formatting selection, and I'm going to select currency. There we go, $547.36. So we can say that $100 today at 12% interest is economically equivalent to $547.36 15 years from today. Those two values are economically equivalent. There's another way to find that $547.36, and the way to find that is using the spreadsheet functions, and the spreadsheet function to find that is called FV, or future value. Let's find out what that future value would be. And if you'll look at the conversion table that I discussed in the last video, you'll see that we should use the function like this, equal to negative, start off with a negative sign. Again, I'll talk more about that in a future video. FV, which stands for future value. First argument is the interest rate, 12%. The second argument of the function is the number of years, 15 years. We're going to skip the third argument. I'll come back to that probably in the next video. So I'm going to put 2 commas to get to the fourth argument, which is the present amount of $100. I'll close out that function. So we have FV, the D2 is our interest rate, 15 is the number of years, and then we skip an argument, and the fourth argument here, the third one we provide, is the present amount. And when I hit return, we'll see we should see $547.36. There we go. It's nice when things happen correctly. So this is the way that we can easily find future values using the spreadsheet function FV. Now, what about this case? There's a cash flow of $20,000 20 years from now. What is the economically equivalent amount today? So this is taking a future amount out in year 20 and bringing it back in time to time 0. Essentially the opposite of what we did up here. So here we have the formula. Notice F equal P times 1 plus I to the n. Well, let's solve for P given F. So we take the 1 plus I to the n, we can divide it over here, and we're left with P on the right. We've got some stuff on the left, and the resulting formula there is P is equal to F times 1 plus I to the negative n, right? Or we could say it's F divided by 1 plus I to the n. That's our formula. The notation would be P given F, find a present amount given a future amount, I% in periods or in years in this problem. That is our notation. So let's look at what our answer would be. What is our answer for the present amount, the present economically equivalent amount of $20,000 20 years from now at an interest rate of 12%? Well, this would equal $20,000 times 1 plus the interest rate, which we know is 12%, and the power is negative 20. Here we go. And again, we can change the format of that to currency. So the present economically equivalent amount is $2,073.34. So that amount is economically equivalent to $20,000 20 years from now if the interest rate is 12%. And of course, if the interest rate were something different, the present amount, the present equivalent amount would be something different. Now, finally, let's solve that using the function that we have available in our spreadsheet. And the function that we use to find a present value is PV for present value. Again, I encourage you to consult the table that you have available. Look for the P given F designation. And here we use equal negative PV for present value. By the way, I capitalize those. You don't have to. The spreadsheet will capitalize those later, but simply the either upper or lower case, PV. Much like the FV function, the first argument is the interest rate. For our problem, it's 12%. Second argument is number of years. Here we have 20 for this particular question. The third argument we skip again, and the fourth argument is the future amount, $20,000. That's how we apply the spreadsheet function, and lo and behold, we get the same value, $2,073.34. So we know how to now convert a present amount to a future amount at any time in the future. And we can take a future amount at any time in the future and bring it back to time 0. We can find a P given F, and we can find an F given P. So that's the first step, is moving money around. I want you to realize one little extra piece of information is that these times are all relative. So for example, if there was an amount of cash deposited 5 years ago, time -5, if you will, and you were to find out its value today, given a particular interest rate, then that value 5 years ago would be a P, and the value today would be an F, a future value, because it's future relative to the initial deposit, the present amount that we have. That is present. A P relative to today, because that is before today. So that's the P. Today would be the F. You'd still have 5 years in between, and you'd solve these problems exactly the same way as if they were time 0 and time 5. They just happen to be time -5 and time 0. So they are relative time. But using this P and this F allows us to essentially move money along the cash flow diagram. If it's in the future and we need it to be at the present, we can move it to the present. If it's at year 10, we have a cash flow at year 10, and we need to move it to year 5, we can find the economically equivalent amount at year 5. And we can move it to the future. So we're moving money, just single cash flows, one cash flow at a time. We're moving them wherever we want along the timeline. We can just pick it up and move it and find the equivalent amount. In the next video, we'll look at the case where we don't have single cash flows, but we have multiple cash flows that are the same, equivalent, uniform cash flows. We handle those in much the same way. We want to collect all those up, however, instead of moving them one at a time. We have a way to collect them all up and move them together and convert them to one single cash flow, either before the series of cash flows or after the series of cash flows. And we'll look at that in video number 6.